All right, we can start.
Okay, great. So my name is Meng. I will be presenting our work on learning to rearrange with physics-inspired risk awareness. So this is a joint work with Yuhan Zhenqing and Meng. Next slide, please. So we know that real-world applications require a robot operating in the physical world with awareness of potential risks besides accomplishing tasks. Many risky behaviors and damaging outcomes arise from the physical process of robot interacting with objects. For instance, the agent may be required to move or run on a slippery ground, and it may fall down, which is very dangerous to both the robot and the humans. And the robot can also be required to push a heavy box, which is beyond its affordance. In some manipulation applications, the agent may be required to stacking blocks into a tower, and the agent would like to stack the lighter blocks on top and the heavier ones on the bottom to increase the stability. So all of these cases require the agent to be aware of some physical properties of the objects it is interacting with. Actually, those are some very informative learning signals to teach the robot to be aware of risks. However, this kind of physical risks have not been well captured in the current definition of goal states of success in some manipulation and navigation tasks. Next slide, please. Thank you. So motivated by this, we propose to model the risk in terms of physical cost over the trajectories in rearrangement tasks. We first compute the amount of virtual physical work the agent spends on pushing an object in each step, and also the accumulated physical work along the whole trajectory. Having this virtual physical work, we can define the step physical cost C of t at each step by normalizing over the history or of the history steps so far. Similarly, we can also define the episode physical cost C of tau over the trajectory tau by normalizing over the physical work over or the successful episode so far. So by incorporating the C of t and C of tau, this kind of physical cost into the reward function under the reinforcement learning framework, we would like to make the agent to be aware of the physical properties of the objects it is interacting with, and also the physical risks. Next slide. So to experiment our idea, we have proposed two novel indoor rearrangement tasks. We implemented them in the 3D simulating environments with physics engine PyBullet, and we borrowed the renderer from the iGibson platform. We built the experiment scenes from the classroom scenes, which allow us to experiment with the pushing tasks. We used the fetch robot with two wheels, and fixing the torso and the arm of the robot only allowed the locomotion. The state space is composed of 3D positions and orientations of the robot and the interactive objects. The action space we use here is a discrete action space, including 4 actions: moving forward, stop, turning left, and turning right, which are parameterized by the maximum wheel velocity of the robot. Next slide. The first task we propose here is called variable friction pushing task. In this task, the agent is required to push a box in front of it to the target region, which is the green one in this figure, and across the floor. And this floor have 2 bands. One band, which is the pink one, have the lower friction coefficient. The other one, which is the blue one, has the higher friction coefficient. And the agent aims to choose a physically efficient trajectory without collisions with other obstacles. To achieve this, we define the reward function here, which involves the succeed reward, which is a large positive number 10 here. And we penalize the collisions with obstacles by a negative 10. And we use a smaller penalty to encourage the agent to push the box to achieve the task. And we also include a 10 penalty here to prevent the agent from just wandering around without pushing the box. We incorporate the step physical cost, the CFT, into the pushing term here to encourage the agent to choose a trajectory with less energy cost, which should be a low friction trajectory. Next slide. The second task that we propose here is called variable mass pushing task. In this task, the agent is required to push 2 boxes instead of 1. The 2 boxes are initialized in the circle region, and they have the same geometry and the same initial distance to the robot, but different weights. The agent aims to push at least 1 box outside this circle region without collisions with obstacles and in minimum physical efforts. To achieve this, we incorporate the episode physical cost, the CF into the succeed reward here to encourage the agent to choose the latter box to push. Next slide. So we will show the.
Meng, you have to wrap up. You're out of time.
Oh, sorry. So this is the training results here. You can see that the with the with the reward we define here, the robot always choose the trajectory with lower friction and always choose the latter box to push. And maybe we can skip the next slide and go to the final one. Okay, so for the future work, we would like to extend our method to the region-based case, where we can correlate the object of appearance with the physical properties, which will allow us to generalize the learned policies to unseen layouts. And also we can learn this physical risk and also some basic policies in small pushing, lifting, and local motion trails, and then compose this simple and lower level policies and inject the priors to some downstream tasks, which can be the complex ones, such as building the towers by stacking the blocks. Okay, thank you. That's all.
Hello, can we start? Can everyone hear us? Hear me?
Yes, you can start.
Okay. Hello. My name is Haruki Nishimura, and
I'm Jean Mercat.
We are from Toyota Research Institute today to present our work on risk bias trajectory forecasting. Next slide, please. Actually, next slide. Yeah, I'd like to motivate this problem and our approach by considering safety critical human-robot interaction tasks, such as this autonomous driving at an intersection scenario as illustrated here. So in this particular scene, a probabilistic prediction model on the Ego robot tells that there is a 95% chance of this bicyclist turning right to result in safe interaction. One click forward, please, for animation. Which also means that there's 5% chance of dangerous prediction that can lead to deadly collision or injury. So this 5% may sound like a small number, but it's actually not, because the outcome can be a deadly collision. So the robot must take this small chance more seriously in order to drive more cautiously. Next slide, please. So how can we make an autonomous robot behave cautiously? Well, prior work has leveraged risk-aware planning as illustrated in this block diagram. However, performing risk-aware policy, this risk-aware planner, at first, can you walk through the animation? Yeah, so this stack works by first taking state and history into account. Then the probabilistic prediction module samples a bunch of trajectories that are plausible for the other agent. Then that's consumed by the risk-aware planner for risk-aware policy evaluation. One more click. So what this risk-aware policy evaluation does is it turns the spatial distribution, trajectory distribution, into a distribution of costs under a given cost function. One more click, which reduces this distribution to a risk, such as the CVAR, conditional value at risk, which usually lies between the expected value and the worst case assessment. One more click. Next slide, please. However, performing risk-aware policy evaluation online is challenging because it relies on finite sampling from the probabilistic predictor, because accurately capturing tails in this cost distribution is non-trivial with few samples. So instead, in our work, we propose to sorry, I think you went to, can you go back one slide? Yeah, thank you, that's perfect. So instead, we propose to consider risk not within the online planner, but within the predictor. So we propose this risk-aware probabilistic prediction in which we bias our predicted distribution from the original distribution P to a biased distribution Q, under which simply taking the expected cost computation results in the same risk value that risk-aware robot wants to evaluate to. Next slide. Thank you. Mathematically, this is achieved by enforcing an equality constraint, as shown here in the space of probability distributions. So we pose an optimization problem that satisfies this constraint to offline learn this biased distribution Q based on a pre-trained generative distribution P and a risk sensitivity parameter or risk level sigma. Next slide, please. At a high level, this risk bias distribution serves as a subjective model of probability, in that it pessimistically increases the probability of undesired outcomes under the robot's policy and the cost function. So now I'm going to hand this over to John to talk about the implementation and our empirical results.
Thanks. Next slide, please. So my colleague here presented that we want to bias or forecast predictions or forecast for the behavior. So how do we do that in practice? We designed a didactic simulation here on the top with the vehicle going from left to right at constant velocity on the random pedestrian that appears in any place on the scene, and that has two modes of behavior. One slow mode that is presented in red here because it would result in a collision, it is high cost, and one fast mode here in green because in that scene it's safe, the pedestrian would cross safely the road. So in that simulation, we trained a CVAE predictor to just predict the unbiased distribution of behavior from the pedestrian. And what we can look at is the cost map in the latent space. In this specific example, the lower right corner is low cost, so it's safe behavior, walking fast. And the upper right corner of the latent space is high cost, is walking slow. What we do in a second time is fix that CVAE and train a risk-aware encoder to bias the latent space distribution predicted by that encoder, such that the decoder would decode dangerous trajectories as the output. What we can see in the lower graph is that as the risk level is set to 0, the predictions, the distribution in the latent space shown as an ellipse with one standard deviation here are large and in blue in the safer zone of the latent space here. And as we increase the risk level, the standard deviation decreases and the mean moves towards a riskier, more costly part of the latent space. So we achieve a good biasing to what we want. But this is a didactic, yeah, next slide, thanks. So this was a didactic simulation, but we can also apply that to real data. So we've trained the same kind of model to predict trajectories in the Waymo Open Motion Dataset. And at risk level 0 on the left here, you can see diversity of predicted trajectories. The agent in green has low velocity and can turn left or right towards the ego in blue. As you increase the risk level, the prediction fall down to only turning right towards the ego and going slightly faster. And as you increase it even further to 0.95 here, the agent is predicted to go really fast towards the ego. Here you see the effect of the biasing towards risk, but have in mind that it's not only a biasing, it's really something that allows you to estimate the risk under that new distribution. Thank you.
Thank you.
Hi, can you hear me?
Next speaker.
Can you hear me?
Yes.
Okay. Hi, I'm Heng and I'm happy to present our work on Gaussian belief trees for probabilistic signal temporal logic. Next slide, please. So the big vision is motion planning under uncertainty, where you have dynamics and observation uncertainty with highly nonlinear systems and many obstacles. And that is not a simple problem, and gets even more complicated when you have complex time specifications with temporal events and time window constraints, such as in signal temporal logic that Lars gave some good examples of. Next slide, please. And so for example, we have this robot here in this environment where the specification is go to goals 1 and 2 in any order within 60 seconds while avoiding obstacles. And the robot has, in the environment on the top left, a GPS region where you can localize. Next slide. In our work, risk is, our notion of risk is defined as the probability of our computed trajectories, our controller not satisfying our time specification. And the problem that we are trying to solve is to find a controller such that the final trajectory satisfies the specification with high probability at each time step, which is kind of a pointwise chance constraint. Next slide. So in previous work, we proposed Gaussian belief trees, which generalizes deterministic motion planning to the belief space with chance constraint guarantees. And in that case, it's A to B planning, where the chance constraint is just collision constraints. Next slide. Next. So we showed that using this methodology, the robot is able to know to go to the GPS region to localize first to reduce its uncertainty before going through dangerous regions in order to obey the chance constraints before going to the goal. Next slide. So that was very good for A to B planning, but what happens when you have really complex time specifications? How do we actually guide our search in a smarter way instead of just planning and hopefully reaching the goal, satisfying the specification? Next slide. So what we propose is an abstraction-based approach where we have a time specification and the environment, and we construct an abstract graph of the environment and specification such that searching over this graph will satisfy the specification. And that goes to a multi-layer planning framework that gives us a risk-aware controller that satisfies the specification with high probability. Next slide. And how that works is we first have some abstraction of the space. It can be a grid-based abstraction as long as it satisfies the kind of the regions of interest have to be in one region on its own. Next slide. And what we do in the multi-layer planning framework is at the high level, we search over this graph and abstraction, and that gives us a sequence of timed and ordered regions. And next slide. Such that the low-level planner plans over this, tries to follow this sequence of regions and grows a tree. And as you can see in this example, because the uncertainty grows too large, it doesn't satisfy the chance constraint, and that is fed back to the high-level planner. Next slide. Where the weights of the graph will be updated, and that gives you a new sequence of regions in yellow, which goes to the GPS region, and the low-level planner plans for grows a tree, and as you can see, when it reaches the GPS region, the uncertainty decreases. And next slide. Then as we grow the tree even more, next slide, we finally reach the goal, goals 1 and 2, by first going to the GPS region and following the time path. And next slide. And this gives us a final trajectory that is a sequence of controls that satisfies the specification with high probability. Next slide. Some preliminary results, we see that in both cases, to reach the goals at the top left and right, the robot first goes to the green region to localize before going to both of the goal regions. Next slide. And some current work that we're working on is what the best way, looking at what the best way it is to guide the belief space planner when we're having kind of a multi-layered framework. And one idea we have is to add measurement region information to the high-level abstraction, or kind of directly planning in the belief space for the high-level planner. And there's both pros and cons to each method, and we are trying to explore what the best way to go about this is. And the second one is, currently we are looking at point-wise risk or chance constraints, and how can we go from point-wise to reasoning about the full trajectory instead. Yeah, and that, happy to take any questions.
Hi, can you hear me?
Yes.
Okay, awesome. Hi, everyone. My name is Aray. I'm a PhD candidate in mathematics at Stevens Institute of Technology. I work with Professor Darinka Dencheva, and my main work is focused on the development of systemic risk measures that can be used for multi-agent systems. Next slide, please. So multi-stage stochastic optimization problem can be formulated in this kind of a nested formulation, as it was already mentioned before in this workshop. So we make decision xt at each time stage t, and it incurs some kind of a cost zt. So at each stage we try to make a decision zt that with xt that minimizes the current cost plus the risk of all of the future cost. And by doing so, for the whole time horizon, we get this kind of a nested formulation. This kind of an optimization problem is usually used for single agents, or where all of these risk measures are defined for random variables, and they are usually coherent measures of risk. So my work mainly focuses on how we can extend this idea to work in a multi-dimensional setting, in a multivariate setting. Okay, next slide, please. So based on the idea of coherent measures of risk, we also propose to use an axiomatic approach to the systemic risk. So we define a functional rho now that maps from the space of random vectors. So you can think of random vectors as representing the random cost, where each component corresponds to each agent. So we have this random vector, which consists of the cost of each agent, and we want to measure the risk of this random vector. So we, just for like coherent measures of risk, we define this kind of 5 axioms, and we call a functional systemic risk measure with preference for smaller outcomes if it satisfies these 5 axioms. So since we're representing the system as a random vector, then this approach would be really suitable if we are working with a team of homogeneous agents. That could be, for example, when they have the same kind of resources and they can share them, or if they perform similar kind of tasks and can substitute each other to complete them. Next slide, please. In order to use these risk measures in the optimization problems, we derive this kind of a really nice dual representation. So the risk can be written as the supremum of the product of xi and x. Here xi, so in coherent measures of risk, when we are working in one-dimensional setting, this xi are usually density functions. So to evaluate the risk of the random variable, we take the supremum over all density functions given in the domain. But when we work in a multi-dimensional setting, what we notice that this xi is not really a density function anymore, but rather some kind of, you can think of it as some kind of a scalarization or like an aggregation function that takes all of the components of x and represents as one value. So all of the xi are non-negative, and we notice that their when you take the expected value of this xi, it becomes a vector whose sum of components becomes 1. Next slide, please. So based on that axiomatic approach, we came to this one special case. So we can consider linear scalarization methods. Based on the axiomatic approach, we take the scalarization vectors from the simplex. That basically means that all of the components should be positive and their components should sum up to 1. So if we have this random vector that represents the cost of the system, then we can scalarize it by some kind of a scalarization vector C and impose a risk measure on it. So we can show that all of it satisfies all of the properties because it can be considered as a special case of the axiomatic approach. And also one of the good properties is that the risk of the system will not exceed the risk of its components. So by aggregating all of the costs from all of the agents and imposing a risk, we can make sure that it will not be overestimated. It will be at most the maximal risk of its components. Next slide, please. And also, when we make decisions, we want our risk measures to stay consistent with stochastic orders. So if we know that X is a random vector and it dominates Y, that is basically X is a smaller cost than Y, then we want our risk measure to also reflect that. So the linear scalarization stays consistent with the linear increasing convex order, which means that no matter what kind of scalarization vector we decide to use, the risk of the X will be less than risk of Y. So this implies that when we're trying to make a decision, then the risk measure will lead us to make a decision that has the smaller cost, essentially. And when I showed you the go back, please, a little bit. So in the nested formulation problem, there are two different approaches. Like we can first aggregate all of the costs and then impose some kind of a risk, or we can evaluate individual risk and only then aggregate. So these are two different approaches that I'm considering right now. But this linear scalarization establishes a really good relation between these aggregations. That is, if we evaluate the risk of the aggregated system, it will always be lower valued, it will have lower values than the aggregation of individual risks. And we actually showed that it works for multivariate average value at risk. And next slide, please. And to sum it up, we proposed a new linear scalarization method and an axiomatic approach that basically can be used as a framework for all systemic risks for multi-agent systems. So the current work and the future work will be the development of numerical methods on how we can estimate this dual variables xi, for example, and then how to choose the scalarization vectors and implement them on resource allocation problem that is designed for a team of robots. Thank you.
Right, maybe we can take a question or two. If you have any questions for the speakers. No questions. All right, since we're very short on time, let's skip that and move on to our next speaker. Yes. Yeah, if you have any questions for the previous speakers, then please don't hesitate to reach out to them.